Okay, in this section, we are going to look at quadratic functions and then modeling those functions. We've actually seen quadratic functions before in a couple different lights, and so this is just expanding on those. Start off with a graph that we're hopefully pretty comfortable with already, which is the graph of y equals x squared. So this is otherwise called a parabola. So we have a couple of notable points about this, which is the domain and range listed, but this minimum right here, we're going to talk about, for every quadratic function, there is going to be either a min or a max, just depending on whether, in this case, the function opens up, or if the function opens down, we'll have a max. And so that point is one of our focuses for today. So if we want to graph these functions, there are a couple ways to do that, but one is to put the function into standard form. So we kind of have that standard form listed here, but it might seem like there's a lot going on because we have generic a, h, and k, right? X is just our variable. So the vertex is that point, that min or max point, basically the point where we're turning around. We go from decreasing to increasing or increasing to decreasing. So that's at hk, which is a benefit of writing a quadratic in the standard form, right? We don't usually see them come in this form, so we have to do a little work to get them there. The vertical line, x equals h, right? Again, vertical x is the same everywhere, but y can change. This is the axis of symmetry. That's because, if we look at the previous one, if I were to cut straight down the middle here, right, it's a mirror image on both sides of the function. So that's going to be the case for all quadratic functions. The graphs of those are going to have some line going right through that min or max, through that vertex, that's going to lead to some symmetry. All right, our graph opens up if the a value is positive, down if the a value is negative. And then our graph, we've talked about function transformations before, right, as far as vertical stretching or compressing, shrinking. So if we have the value of a in front here, well, at least the absolute value, right? So the positive, negative is going to affect up and down, but the absolute value of that number, if it's between 0 and 1, we're going to get a vertical shrink, meaning the function is not growing as fast. But if that a value, if the absolute value is greater than 1, we're going to get a vertical stretch because the function is now growing faster. The y values are getting larger faster. Okay, so we're going to start off with a graph, and we're going to try to work our way backwards. We're going to figure out what is the equation of this quadratic based on the graph. So the first thing we'll notice is, all right, this max that we have up here, this is the vertex. All right, so the vertex is the point -3, +4. -3, +4. And if we go back to this previous kind of general page, if the vertex is h, k, that means that we know two of these pieces, right? We know x minus h, and then we have our plus k. So we're trying to get the general form, and maybe I'll put that up at the top. So we're trying to come up with some function, a times x minus h squared plus k. So we just found h and k. So that's great because the only thing left for us to find is a. So we've got to think about, okay, well, what do I know about a? So for example, this opens down. So that would say that a is negative, where a is less than 0. And then the other piece is we got to figure out if there's any stretch to this. So basically from our regular quadratic, do the points that we find, do those sort of make sense? Okay, well, our standard quadratic here passed through the point 0, 0, and then we went over 1, up 1, to get the point 1, 1, and to the left 1 and up 1 to get -1, 1. Okay, so we'll start off, we'll look at that, and we'll say, okay, well, I went over 1, and because we're opening down, instead of going up, we go down 1, and to the left, and down 1. Okay, that seems to check out. The next points, we go over 1 and down 3 in each direction. So if we opened up, I guess we would go over 1 and up 3, and sure enough, that's how we got from 1, 1 to 2, 4. So it looks like there's no stretch or shrink. And so what that means is that our A value is going to be -1, the negative because we're opening down. And then because there's no stretch or shrink, we don't want to include some other factor in front there. So our overall conclusion then would be that our function looks like negative or -1, if you prefer to put the 1 there, that's totally fine. X minus h, so h was -3, squared, plus k, which is 4. Okay, we can probably clean that up a little bit. So negative x plus 3 squared plus 4. Okay, so that's fine if we start with the graph, but what if we start with a function and we need to get it into that standard form so that we can graph it? Well, we need to do something called completing the square. So the steps for completing the square are listed here. We're going to kind of walk through those in an example. So I can maybe refer to this page so that it's not just something you're memorizing, but of course you could you could write this down if you wanted to just have it in your notes so you don't have to refer back to this video. So we're going to take something of this general form and use the coefficient of the x term, so that's b. We're going to divide that by 2 and square it. So this is b over 2 squared. So let's take a look at our example and do that. So here, the coefficient for the x term is 6. So we're going to say 6 over 2, and we're going to square it. So that's 3 squared, or 9. Okay, at the moment we might kind of wonder, I'm not sure what we're doing with that. So add that number, the number we just got, next to the x term, and subtract it from the constant term. So we have to add it and subtract it, basically so that we're not changing the function that we started with. So we've got f of x is x squared plus 6x. And then we're told, okay, take that number we just found, b over 2 squared, so 6 over 2 squared, add it after the x term, and then subtract it after the constant term. So we added 9, subtracted 9. So this is the same exact function as what we started with. It just looks a little bit different. Okay, so we've done those first two things. Now factor the first 3 terms. All right, so that looks like f of x is going to be, we've somehow got to factor these first 3 terms. So I'm going to toss in some parentheses there. So we've got to factor those first 3 terms. It turns out that we would get x plus 3 squared, and you might need a little bit of reminder as far as how we factor something like that. But we've done plenty of those, so I'll refer you to the videos on factoring if this is unclear. And then we can combine our constants over here. So we say plus 1, right? 10 minus 9. So now we kind of have something of that general form where we could say, hey, a is just 1, x minus h, so I guess h is -3, and then k is +1. And then we want to describe the transformation of the graph. So y equals x squared is the most basic quadratic function. We want to say, okay, what did this function do to that? Well, the x plus 3 portion, that shifted it to the left 3 spaces. So this is a left shift or a horizontal shift left. by 3. And then the plus 1, k being plus 1, that just means we shifted it up. So up by 1. So those are our two transformations. And that's also why the vertex ends up being at h comma k, because we shift the entire thing, and originally the vertex is at the point 0, 0. So however far we shift, we go to the left 3. Okay, so there's -3, and then up 1, positive 1. Okay, so here we have the exact same function. We're just continuing the example. So let's sketch the graph of f of x. So maybe we want to remind ourselves what f of x was. So let's just rewrite what we had here. It was x plus 3 squared, and then plus 1. F of x is x plus 3 squared, and then plus 1. We said our vertex was -3, positive 1, right? Because we shifted the original vertex, well, we shifted the entire function to the left 3 and up 1. That's what we said in part B. And because a was just 1, right? We don't have any number in front of x plus 3 squared. That means that our proportions are pretty much going to stay the same with what we're used to. So we're still going to open up, and we're following kind of that same pattern that we had before. I'm putting a few points on here, but you don't necessarily have to do that. I'm kind of echoing the fact that from the vertex, we go over 1, up 1, and then over 1, up 3. So I was just putting a couple extra points in there, but you don't necessarily need to add all of those in there. So, all right, we have this function, and it looks, again, with some curvature. I apologize, my graph is going to be a little messy, but it looks something like this, right? Should pass through the points a little bit better than what I did, but something along those lines. Opens up, it's not stretched or shrunk at all, but it is shifted over and up. All right, so give the minimum or maximum value. Well, because we open up, we're going to have a min value. So the min value is the y value, right? We could say what is the vertex, which would be the point. But here we're just wondering, hey, what's the minimum value? So the minimum y value is positive 1, right? The smallest y that we can get. All right, give the interval or intervals where the function's increasing. Well, at first we're decreasing. We get down to the vertex here, and then we start increasing after that. So from -3, and we give the x values, right? So from -3, this x value of -3 onward, we're increasing. Infinity always gets a parenthesis. -3 is also going to get a parenthesis because exactly at -3, we are neither increasing nor decreasing, right? We're at that turning point. We go from decreasing to increasing. Okay, we've got another function here that we're basically trying to do the same thing that we've just done, which is, figure out f in standard form. And we can refer to our kind of completing the square steps, and we'll see, what exactly that looks like. So if we take the coefficient of the x term, so that's b, divided by 2 and square it. Let's give that a shot. So in this case, that's 8. So we're going to say 8 over 2 and then squared. So 4 squared, 16. All right, we're going to add this within the function f of x. We're going to add it after the x term, plus 16 there. And then we're going to subtract it after our constant term. Again, so that we're not changing the function at all. Whatever we add in, we're taking back out. From there, we're supposed to factor the first 3 terms. So we're going to say, okay, those first 3 terms, I can definitely take a -2 out of there. Get x squared plus, oops, sorry, not plus, minus. So if we factor out a negative, right, all of the signs in here are going to change. So minus 4x and minus 8. And you can double check just by distributing. So -2 times each of these, does it get it back to where we started? And then the two constant terms, we can put those together, so minus 21. And from here, we can say, great, let's keep going. We haven't yet factored. So how do we factor x squared minus 4x minus 8? So this thing does factor into x minus 6 and x plus, oops, sorry, not that. Oh, actually, right. So this is an adjustment that we need to make actually to our method here, and I meant to point that out. So this is if the coefficient, so this is here at the bottom. If the coefficient of the x squared term is not 1, factor it out first from the first two terms. So sorry, that was a little bit of a mistake. We're still going to need some of this process, but I'm going to start us over here. So we can just kind of clear out some space for us here. So right, if we have a coefficient other than 1, we can factor that out. So the very first thing we're going to want to do is factor out -2. So f of x is -2, and then x squared minus 4x. So just factor it out of the first two terms. You can leave the constant term alone. Okay, and now it's on this inside stuff that we're going to want to complete that square. So we can say, all right, let's just focus on that, x squared minus 4x. So we have our b value is -4. So we're going to say, all right, I'm going to add -4 over 2 squared. And then I'll subtract that back out, and I'll kind of show us, how we do that in just a moment. So I'm just going to focus only on completing the square here for a moment. So if we do that, we get x squared minus 4x, and then -4 over 2 is -2. If I square it, the negative is going to come out. So I get -x squared minus 4x plus 4. All right, so let's go back to the original function. I have -2, and then inside here I've got x squared minus 4x plus 4, and then minus 5. Okay, so how does this compare to the original? Well, I just pulled this plus 4 essentially out of nowhere, right? I just threw it into my equation. So we've done this with completing the square. We kind of have to balance things out. So we might think, hey, let me just put, if I added 4, let me just subtract 4 here. Okay, the problem with this is the -2 out front. We still have to account for that. So we didn't really add 4. We actually said, oh, -2 times 4. So we actually contributed -8, right, out of thin air. So how do I balance that out? I actually balance that out by adding 8 back in, right? So let me do that in another color just so that we kind of see, right? So here's what we added. We added from thin air, -2 times +4. So to balance that out, we have to, right, undo it. So -8 gets balanced out with +8. Okay, so now let's factor what we have in the parentheses. And the goal, the reason I knew the first time around something wasn't quite right is because the stuff in the parentheses here, when we factor it, should be a perfect square. That's why it's called completing the square. If we don't get a perfect square, something's off. So we got x minus 2 squared, and you can double check x minus 2 times x minus 2 will get us back to what we have in the parentheses here. And then the constants come together as +3. So now we have everything in standard form, right? We know that our a value is -2, our h value is +2, and our k value is +3. So our vertex, right, is h comma k. So 2, 3 is our vertex. So let's go to 2, 3. There's our vertex. And this is what we're asked to do, right? Sketch the graph. This is going to open down, which we know because A is negative. So that's maybe worth pointing out. So open down. And then it's going to be stretched by a factor of 2, right? So if we have a number out in front here, that's our stretch or shrink. Since it's greater than 1, it's going to be a stretch. So normally we would go over 1 and down 1, right? Over 1, down 1. So normally the points would be here and here at 1, 2, and 3, 2. Normally, that's the case. Okay, but the vertical stretch says that we need to basically go twice as far away. So we go over 1 and down 2, over 1 and down 2. So we're going to get something that's a little bit more stretched out than what we're used to seeing for our parabolas. So we get something along these lines, and it should have some nice curvature. Again, it's a little tough when I'm drawing these on the tablet here, but it should have some nice curvature to it, and just be stretched out a little bit more than usual. So as one more reminder, right? Keep this note in mind. If the coefficient is something other than just 1, we've got to factor it out first and then operate from there. And we'll definitely do an example like that in class. Okay, so finding the vertex and the intercepts graphically, right? We have this technology to help us out, so it's worth trying to leverage that and say, hey, you know, can I use a calculator to help me out? Absolutely, you can. So here are all of the steps. We're going to walk through an example where we kind of see, can we follow these steps and actually work on a specific function, and hopefully that'll make a little bit more sense. But you may also want to just, you know, kind of jot down these steps while you're getting used to it. Like anything else, if we do this a couple times, you'll have it totally down. So here's our specific example, and we're going to go through those graphing calculator steps to make sure that this hopefully all makes sense. So we're going to find the vertex and intercepts for the quadratic equation given. And notice this quadratic has a coefficient in it with the square root of 2. So yeah, maybe things like factoring, completing the square, all of that might be a little bit trickier. So that's one reason we might use a graphing calculator. So let's check those steps. So we're told, okay, first of all, put the equation into y1. So let's go back to the equation. Here's our function. In our calculator, let's click y equals. The very first one is y1. So we can do 1 plus x, and the x button is going to be the one that has x and t and theta and n. So 1 plus x minus, the square root is going to be above this x squared button. So we hit second and then x squared. We're just going to put 2 in there, and then make sure that you're not still under the square root. So we've got to click the right arrow for x squared, because notice that is not under the square root. So, and then we hit x again, and then the same place we found the square root, but without hitting the second. So just the square button. Okay, so there's our function. It's in y1. Great. Let's go to the next step. Adjust the viewing window so that you can see both the vertex and the x-intercepts. Okay, well, let's just go graph this function, and usually the window is a standard window, so I'll kind of just put us on the Z standard here. So this window is fine. It goes from -10 to +10 in both the x and y directions. We can see the vertex, we can see the x-intercepts, but maybe not super closely. So if you want to adjust, just click window, and maybe you only want to go between, you know, -5 and +5 for the x direction. Maybe you want to go between -2 and +6 in the y direction. I don't know. Let's take a look. All right, so this is a little bit more zoomed in. If you want to really zoom in, that's fine. You know, we can go between -1 and +2. You know, we can kind of adjust as we need, but this is perfectly fine. We get a sense for what this looks like. Okay, to find the vertex, so we're on to the third bullet here for our process. To find the vertex, press second trace. Okay, so we see the trace button up top here. So second trace, and where it's really bringing us is calculate. So we want to choose a minimum or a maximum depending on the graph. Well, our graph opened down, so that means we have a maximum. So we're going to either scroll down to 4 or press the number 4 and then hit enter. It's going to ask you, hey, what's your left bound? And that's exactly what the next step says here. Move the cursor to the left of the vertex. It already is. So I can just hit enter. What's your right bound? Okay, we've got to press the arrow key just so we're on the other side of the max. Hit enter. And then it'll ask you for a guess. Now, if you want, you can move the cursor close to what you think is the max. Otherwise, you can usually just hit enter again and it'll be totally fine, especially when these values are pretty close together. So this point, the maximum, 0.3535, blah, 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 and y equals 1.767767, etc. So that's our vertex, right? X comma y. So let's go and fill that in for our vertex. So we've got the point, right? It's a point, so the x value, 0.35, and I'll just round maybe to 3 decimal places, so 354. And then the y value is 1.177. Again, if I round to 3 decimal places. Oh, I said 2 up here. So I guess 0.35 and 1.18. Sorry. All right, always be careful in the homework. You know, it's not too much of a big deal if I'm writing out these examples, but you know, be careful about the homework. It will be kind of picky about however many decimal places it specifies. Okay, let's go back to our directions. So to find the x-intercepts, put 0 into y2. So this is one way to do it. So put 0 into y2, and then hit second trace intersect. So basically we're going back to the same place we did before, the calc portion, so second trace. And we're looking for a 0, right? Or sorry, we are looking for rather an intersect. So the intersection of the two functions that we have graphed. So the first curve, right, move the cursor to one of the x-intercepts and press enter. So, okay, we're gonna press enter right here. And the second curve basically should just put us on the other function that we have. And then we can just hit enter for our guess. So this says the intersection is -0.5586, blah, blah, blah. Okay, and then our y value is 0, as it should be if it's an x-intercept. So we're gonna say, all right, -0.56 if we're doing 2 decimal places, comma, 0 for x-intercepts, right? So we have an x value, we have 0 for the y value. Of course, there is a second 0 for this. So let's hit second trace again, and we'll go back to intersect. And so let's kind of scroll closer to our next 0, or our next x-intercept. So our first curve is y1, our next curve is y2, and you'll see up in the upper left-hand corner that it specifies which curve is which. So when it says first curve, second curve, make sure you're choosing y1 for the first one and y2 for the second. And then your guess, yeah, I mean, you can guess, you can scroll over, or you can just hit enter again usually. And this will give you a new intersection, right? So we have 2 x-intercepts. So let's come back over here and say, cool, we have that as an x-intercept and the point 1.27, right? We'd round that up, comma 0. And the directions don't specify here, how do I get a y-intercept? Well, all right, getting a y-intercept just means that x is 0. So another way to say this is let's find f of 0. So let x be 0. That means 1 plus 0 minus 2, sorry, square root of 2 times 0 squared. Well, that's going to be 0, that's going to be 0. So I guess we end up just getting 1. So we have the point 0, 1. That's our y-intercept. And you could check that on the graph too in your calculator. The other thing I wanted to point out here is let's go back to second and then trace so that we're accessing the calculate. You can try the 0. So the 0 for that function, if we want a left bound, so we're sticking with the function y1. The left bound, I'll put it to the left of this 0 here. And the right bound, I'll put it over here and hit enter. I guess I can just hit enter again. And it's going to give me that same number we just got, 1.2657, whatever, so 1.27 that we got for our X intercept. So that's another way to do it. You don't necessarily have to plug in y2 equals 0 and find the intersection. You can just find the zeros of the function. So both of those methods are perfectly fine. Okay, so when we're finding the vertex of a function, of a quadratic function, we can cut straight to the chase. So we have a nice way of finding this. The x value of the vertex is always going to be negative b over 2a. And then the y value is just plugging that number back into the function, right? So we're just taking that x value and saying, okay, find f of that, and that'll be your output, otherwise known as your maximum or minimum value, depending on whether you open up or down, right? So if you open up, our vertex is going to be at the min. If you open down, our vertex is going to be at the max. So if we have a function like this, let's find the max or min value. So first of all, the a that we have, a is just 1, positive 1. That means we open up. Okay, I guess that means we're going to find a minimum value, right? If we open up, we've got a minimum value. So that's good to know. Our x value is going to be negative b over 2a. So b is already negative. Be careful about that. So negative 2, or the opposite of negative 2. Then 2 times a, we said a was 1. So on the top we have positive 2, on the bottom we have positive 2. So the x value is 1. Okay, we're not quite done. We just found the x value for the vertex, but now we need to find the y value. So the y value is going to say, okay, plug that value of x that you just got, plug it back into the function. So 1 squared minus 2 times 1 plus 3. And that looks like 1 minus 2 plus 3, otherwise known as 2. So the vertex is the point 1, 2. The minimum value is the y value that we got, so 2. Okay, here's one where we actually have an application. So we have the gas mileage function for a car traveling at a certain speed. So S is the speed that we're traveling, M is the mileage. And so we want to know, all right, what's the best mileage? So the maximum gas mileage, miles per gallon. So we want to know essentially what's the vertex for this thing. So let's find what we would normally call the x value, right? But here it's s, our variable is s. So we can use the same formula, negative b over 2a. So b in this case is positive 3, so this is negative 3. A is negative 1 over 28. Okay, so this we can calculate. First of all, the negatives are going to cancel out, so that's a good thing. But if we want to calculate this thing, maybe we'll actually pull up a calculator or something to do that. I'm going to do that off screen real quick, but it would probably be a good idea for you to verify what you got. I would say be careful about using parentheses as you're working through your calculator. So if you don't get the same answer as me, maybe double check how you did that. So in this case, I got that S was 42. And this is 42 miles per hour, right? Or mph if you prefer. but in this case we're doing miles as mi and hours per h. So this is s, a speed. So first of all, that should make sense. Driving 42 miles per hour is a relatively modest speed, right? We could certainly go much faster than that. And it makes sense, right? We didn't get like 0.4 miles an hour or something, or 400 miles an hour. So we got a reasonable speed. That seems to make sense. So that's the speed where we attain our best mileage, but we need to go find our mileage. So let's go find the mileage at 42 miles per hour. So if we're driving 42 miles per hour, we're wondering, okay, what do I get? You know, mileage measured in miles per gallon. So we're just plugging in 42 in place of S. And again, I'll do this off screen, but it would be worth, you know, for you to check that that's actually the case. So let's see. Again, just kind of plugging this in off screen here, and I end up getting 32. So 32 miles per gallon, which again is fairly reasonable. A lot of cars are sort of in that 20 to 40 miles per gallon range. If you have an older car or you know, a truck, something like that, maybe it's below 20 miles a gallon. If you have a car, a hybrid or something like that, it's going to get probably closer to like 50 miles to the gallon, 60 miles to the gallon. So at least this number feels fairly reasonable. So our best mileage is 32 miles per gallon, and at what speed? 42 miles an hour. That's where we attain it. Okay, and then finally, we've got an example where, you know, we definitely want to draw a picture for this one. So a homeowner has 80 feet of fence to enclose a rectangular garden. Okay, so we have no idea what this garden looks like. So I'm going to call this X and this Y, which of course means that if it's a rectangle, the opposite sides are the same. So we want to know what dimensions for the garden, meaning what is X and what is Y, what dimensions for the garden give the maximum area. So we want to maximize area, right? X times Y is the area of a rectangle. We would like to maximize that, meaning, what does that mean? Well, we've been finding max and min values, so maybe that'll help. But right now we have two variables. Okay, we've been working with one variable, right? X is our input and then Y is our output. We can't have X and Y as inputs and then A is an output. So too much going on the right side here, right? Two variables where we should have one. So we have to use this other piece. There are 80 feet of fencing. So keep in mind the perimeter is going to be X plus Y plus X plus Y, otherwise known as 2X plus 2Y. And that's supposed to be equal to 80, right? And maybe it'll help if I write that side by side. So 2X plus 2Y equals 80. So this is sort of like your original constraint, right? Well, okay, we could solve for one of these variables. So I could say 2Y is 80 minus 2X. And then I could divide everything by 2. So I get Y by itself. So Y is going to be, well, 80 over 2 is 40. And 2X over 2 is X. So 40 minus X is the relationship, the fixed relationship between X and Y. So I'm going to come back over here to my area and say, okay, I can replace Y now with 40 minus X. Why is that a good thing? Well, if I distribute 40x minus x squared, oh, hey, wait a minute, this is a quadratic. And in fact, it's a quadratic that opens down because my x squared term is negative. So that means we're going to have a maximum value. So there's a couple ways we could do this. But let's pull up our calculator one more time. We might as well just see what that looks like. Okay, so if we open up y equals, right, and we just have to go to the y equals button in the upper left here, put in our function 40x minus x squared. And normally we would want to adjust our window. I adjusted mine already. So sometimes you have to use the zoom. So if you click on zoom in the middle, you can zoom out or zoom in, do what you need to do. But I adjusted my window if you want to adjust yours to look the same. I kind of knew where this was headed, but sometimes you got to play around with it a little bit. So let's go to the graph, right? We get a function like this. Hey, it's a parabola like we expected. It's opening down, all good. So if we want to find the maximum, right, the max up here or the vertex, let's go second trace. And maximum is the fourth one. So either scroll down to 4 or hit 4. The left bound, let's go a little bit to the left of the maximum, hit enter. A little right to the maximum, hit enter. Right, notice those two arrows are saying like, hey, your max should be somewhere between these. Your guess, you can either move the scroller again, or you can just hit enter right away. That's fine. So if we do this, we get our maximum is 20.0000. Okay, there's a number out here, but basically if you see either a bunch of zeros or a bunch of nines, it's saying like, well, I'm a calculator, I'm not perfect. So I got as close as I could with the algorithm that I use. So really it's 20, it's just 20 on the dot. So X is 20, Y is 400. So what that means is we have a vertex over here. Oh, this, or vertex is 20, 400. But let's be careful about what it was we were finding. The input was X, right? That was a width. That was one of our dimensions. The output was not Y, right? We said area. A was our output here. So 400 is the area. 400 square feet is the max area. But this question asked about dimensions, not area. So that means we need to know X and we need to know Y. So X we already said was 20 feet. And then Y, we have an equation here in the sort of cloud connecting X and Y. It's 40 minus X. So 40 minus 20, or 20 feet as well. So that means that both our X and Y are 20. Really all that's saying is the most efficient rectangle is a square, which maybe isn't super surprising. But this won't always be the case, right? Our dimensions are not always going to be the same. That just happened to be the case in this example. And I will say, you know, be careful about your calculator says X and Y. If we actually made the Y value in our problem 400, we'd have way more than 80 feet of fence. So be careful about what it is we're measuring, right? What's our input? That's the width. What's our output? It's not the length, it's actually the area. So, all right, that's that.